In this video, we'll discuss the developments of analytic geometry and precalculus during the 16th and 17th centuries. Now let's start with the concept of analytic geometry. This is the ability to explore geometric concepts through algebraic means, and this became more prevalent during the 16th and 17th centuries thanks to new symbols and processes that were being constructed. Now, we think about what is analytic geometry. Let's take just the idea of points and lines. A point we would think of as a location on the coordinate plane. Once we write that as an ordered pair, we've turned that into an algebraic process. Lines being defined as something like slope-intercept form or standard form, that is an algebraic means to something that is geometric. Much of this work we credit to Descartes and Vermont for inventing these different concepts. Now, Rene Descartes was both a philosopher and a mathematician. If you've ever heard "I think, therefore I am," that dates back to Descartes' work. However, he is well known within mathematics for his work in analytic geometry, and it's said that it began to come to him when he was stationed in the army on a cold night. A lot of the work that Descartes did was often in bed, which sounds like a very weird place to be doing your mathematics. He also did work in the universe, but once Galileo was under house arrest by the Catholic Church, he stopped his work because he did not want to end up in the same situation. And he turned his work back to working on his mathematics, such as the analytic geometry. That allowed him to create books such as La Géométrie, which focuses on analytic geometry. So in the first part of La Géométrie, he worked on constructing variables. If we think previous to this, the Greeks initially said that a variable was the length of a segment, the product was the area of a rectangle, and the cube of a number would have been represented by the volume. So this is all geometric. Whereas Descartes comes in and puts it into this concept of an algebraic concept, where a variable will become a proportion. And that ability to construct it as a proportion allowed for the construction of any length for any power of a product of x. In part 2 of La Géométrie, he worked on constructing tangents to curves, but the mathematics has such improved that this has become obsolete. And in part 3, he worked on the rule of signs, which we still do teach in algebra courses, which is the ability to determine how many positive and negative and complex roots there should be in a polynomial. Now, how is this done? What we do is we look at how many sign changes there are in the polynomial when we have the positive x or when we substitute in the negative x. And we can then create a chart showing what are the possibilities for the signs and the number of roots in this given polynomial. So let's look at an example. Say that we have f of x equals 4x to the fifth plus 3x to the fourth minus 2x cubed plus 5x squared minus 6x plus 1. Now here we have every order of x in the equation. We wouldn't necessarily need that as long as they're in numerical order, starting with our highest power. Now for the positive, we're looking and saying, how often does the sign change? If I go from the first term to the second term, this would be no. If I look at the second to third term, yes, that goes from positive 3 to negative 2. From the third to the fourth, yes, that's negative 2 to positive 5. Positive 5 to negative 6, that's a yes. And then negative 6 to positive 1 is a yes. So there's 4 sign changes there. So there's a possibility of up to 4 positive roots. Now when we look at the negative, we're going to substitute in negative x wherever there's an x, and we're going to simplify each of those statements. Negative x to the fifth will make a negative 4x to the fifth. Whereas negative x to the fourth, that's always going to become positive because it's an even index. So that stays plus 3x to the fourth. Negative x cubed will create a negative value, so negative times a negative becomes positive 2. Here, negative x squared is always positive, so that's still positive 5x squared. Negative x times negative 6 gives me positive 6 and plus 1. Now we look at the sign changes again. We go from negative to positive, yes. But this is positive to positive, no. Positive to positive, no. Positive to positive, no. And positive to positive, no. So there's only one possible negative root. So now we work on creating a chart to help us understand this. So if we start with our greatest situation here, we'd have 4 positive roots, 1 negative root, and since the index is 5, that would mean there are 0 imaginary roots. Now that's not the only possibility. So I want to decrease by 2 my options of positives. The negatives I can't decrease anymore because I'm already at 1. So it will be 1 negative root within this polynomial. So if I go to 2 positive roots, there'd be 1 negative. Well, I still have to add up to 5. That would mean that there'd have to be 2 imaginary roots. And if I can subtract 2 one more time, I see that 0 would be a possibility because I either have 0 or 1 as my final options. 0 positive roots would give me 1 negative root. That would mean there'd have to be 4 imaginary. These are the 3 possible options. We don't know which one it is until we actually go through and solve for the roots, but these are the possibilities, so we know as we're going along, oh, if I get this many, if I'm already up to 1 positive root, I know there's got to be at least 2. If I find a 3rd positive root, I know there's 4. So it helps to reaffirm what we may be doing as we're solving the problems. Another famous mathematician at this time was Pierre de Vermont. He was actually a judge by occupation and did mathematics as a hobby, which is kind of unique when we think about all the mathematics that Vermont was able to do and how well renowned he is in mathematics. He examined analytic geometry in a little bit different way than Descartes, where he started with the equation, then would study it geometrically. So they were able to bring in different concepts and ideas because of the way they looked at the analytic geometry concepts. He was able to construct equations for parabolas, hyperbolas, and even the spirals of Vermont. And he's also known for his modern day, what we think of as number theory. He founded and discovered many of the concepts that we utilize in that field. So here's a couple examples of Vermont's number theorems. We have his little theorem, which states that if p is prime and a is relatively prime to p, then a raised to the p minus 1 is divisible by p. Just to show what that means, say we say that we have our prime number of 5, and 8 is relatively prime to 5. So if I did 8 raised to the 5 minus 1, so 8 to the 4th, and then I subtract 1, I would end up with 4,095. That is divisible by 5. That's what Vermont's little theorem was stating. Now, he also had Vermont's big theorem, or his last theorem. And what this states is there does not exist positive integers x, y, z, and n such that x to the n plus y to the n equals z to the n when n is greater than 2. Now, this was a huge deal, and it was a huge deal for hundreds of years because Vermont never proved it, even though it was recognized to be a true statement. He wrote in the side of one of his books, "I have assuredly found an admirable proof for this, but the margin's too narrow to contain it." It was seen at that time as maybe he had the idea but just couldn't prove it, and this was his way to get out of that. Now, what is unique is that this was not proven until 1995. And the proof that Dr. Andrew Wallace created for it was over 100 pages long, and he spent a lifetime trying to come up with this proof. Another famous mathematician at this time was Bache. He created the problème plaisant, which is where many of our types of puzzles and number games that we have today come from. He also translated Diophantus's Arithmetica to Latin, and it is in that book that Vermont wrote the last theorem and some of his other famous notes that he would put in the sides and the margins of his books. And finally, let's discuss Christian Huygens, who was a Dutch astronomer and mathematician that improved the lenses of telescopes, constructed the pendulum clock and the mathematics behind how a clock works, as well as wrote a formal treatise on probability after the work that Fermat and Pascal did on the problem of points. He also worked on the wave theory of light after he met Isaac Newton. So let's look at his idea of probability. So what Huygens determined was the mathematical expectation, which we also call the expected value. What he determined is that the probability P of winning some amount of money can be determined by taking that sum and multiplying it by its probability. Additionally, if there are multiple ways to win, then the probability of each of those times the sum of what it could win will equal the total expected value. And that is over the long term of playing the game. It gives you that average of what would you expect to win each time over a long period of time of playing. So let's look at an example. Suppose a gambler will win $3 if a 6 is thrown, or $1 if a 1 or 2 is thrown on a single die. And they want to know what is the mathematical expectation. In other words, what's the expected value on average over the long term when this game is played. So start with, what's the probability of rolling a 6? Well, on a 6-sided die, each number has an equal chance of being rolled. That means the probability of 6 is 1 out of 6. That would also mean that a 1 or 2, there's 2 options out of the 6. So now we take each of those, multiply them by the sum they could win, and add it together to give us our expected value. So this would be the probability of rolling a 6 times the $3 for winning, plus the probability of rolling a 1 or 2 times the $1 for winning. So we'd have 1/6 times the $3 plus 2/6 times the $1. That would give us about 50 cents plus 33 cents, because our money only goes to 2 decimal places. That would mean that the gambler on average would win about 88 cents when we add those two values together.